Hello everybody. My name is Mr. McAllen, and I'm going to be working today to show you the chain rule done the traditional way, and then my next video will be the chain rule done, I don't want to say the non-traditional way, but done in another way, which is by using the onion rule. So I'm going to start out with just a brief explanation on the traditional way using the Leibniz notation. So what we want to do is first let's imagine that y is a function of x is a function of a function made up of several parts all composed with each other. For example, y is a function of u, which is has a function in this side of it. That's a function v, which has a function inside of it called x. So when you have a function that is made up of several layers, it's important to understand that when you want to find its derivative, you start from the outside, you take the derivative with respect to u, evaluate it at the inner, times the derivative of u with respect to its inner, with its inner function plugged into it, times the derivative of its inner with respect to x. So what we see here, when we have 3 layers deep for a function, we have 3 links in the so-called chain for the chain rule. If you notice that when we multiply these links by each other, the v's will cancel, the u's will cancel, and we'll be left with pardon me, what we're searching for, dy dx. Now, looking at our first example, we see that we have 2 layers that the function has for depth. The first layer is sine, the second layer is 3x plus 1. So we want to write up our functions such that we have y as a function of u as a function of x. So we'll write up y as a function of u is just going to be the sine of u. And u as a function of x is just going to be 3x plus 1. Now, based on the way that this chain rule would work for this problem, since it's 2 layers deep, we need to take the derivative of y with respect to u multiplied by du with respect to dx. So that's pretty easy. Dy du is cosine of u, and du dx is just plain old 3. As the function says here, we multiply the derivatives by each other, so we'll have 3 for dy dx, we'll have 3 cosine of u. Now remember, we started out with y as a function of x. We'd really like a derivative to be a function of x. So we want to do a replacement here, a resubstitution, and write this as 3 times the cosine of 3x plus 1, merely substituting in what u of x was equal to. On our next example, we have a function that is 3 layers deep. There's layer 1, layer 2, layer 3. And the problem here is most people think that the layer 1 and layer 2 are switched, but this function actually is shorthand notation, and we should write it as, or think of it as, the sine of 3x plus 1, that whole quantity squared. So once you have that type of notation in mind, or correctly thought out, you can write out y as a function of u is equal to u squared. U as a function of v is equal to the sine of v. And v as a function of x is equal to 3x plus 1. So then we take our derivatives. Dy du is equal to 2u. Du dv is equal to cosine of v. And dv dx is equal to 3. Now we just multiply these by each other, and our total derivative will be dy dx will be 2u times cosine of v times 3, bringing the coefficients out in front. I'll have 6u cosine of v, and doing my substitutions, I'll have 6. I'll substitute back in for u. I'll substitute sine of v, and I have cosine of v, and now I'll make my last substitution where I'll substitute the 3x plus 1 in. And that would be my final answer. For the last problem, I have a product rule problem, and I'm just going to rewrite it. It's y as a function of x is equal to x cubed times 2x minus 4 to the 4th power. Now this one we're mixing the product rule with the chain rule. This is my f function. I'll call this my g function. The derivative would be equal, the derivative of the first times the second, plus leave the first alone, times the derivative of the second. So just for explanation purposes, I'm going to write out what my f and my g functions are. So f is equal to x cubed, g is equal to 2x minus 4 to the 4th. My f prime is easy, it's just a simple power rule, but my g prime requires a chain rule. So what I'll do is, I'll just think of g as a function of u, and u as a function of x, taking advantage of what I've just done in the previous example. U to the 4th, and u as a function of x is 2x minus 4. I'll write out what g prime, I should say dg, du is, that would be 4u cubed. Du dx is also simple, it's just a simple power rule, that'll be 2. Multiply these together, resubstitute my u, so I have 2 times 4u cubed, resubstitute my u component, and now I'm going to, which would make 8 times 2x minus 4 cubed, and now I'm going to just put that in this part here. I'll zoom out so we can see everything. So f prime g plus g prime f from up above using the components. I've got 3x squared times the quantity 2x minus 4 to the 4th power plus g prime f, which it says is 8 times 2x minus 4 cubed times the f component, which is x cubed, and that would be my derivative. Now, some kids may say, what can I do from this point as far as simplifying and everything else? I just want to point out a couple things. There's an x squared in both terms. Like there's an x squared that can be taken out of both. And there's also a quantity 2x minus 4 that can be taken out of both terms. So there is plenty of simplifying that can be done from this point, but the objective was to show you how you would get an answer for the product rule where you have the chain rule built in. This concludes my video for doing the chain rule the traditional way. So what I'm going to do is process this video and then make another video which shows the comparison to doing the chain rule from the outside in. And that hopefully will take a little bit less time, but it will be equally informative as far as how we can move quicker through the chain rule. Thanks for watching. Please feel free to comment on the YouTube channel to let me know if there's any things that you think would be helpful to you in the future.